Hello everyone, welcome to this introductory lecture on Introduction to Causal Inference. I'm Dheeraj Madan and I'll be conducting this lecture. So just a word of caution is that I'm myself learning this area, and this is something new to me, so I'm not an expert in this area. And today's lecture is going to be an introductory one, but later we might go into some of the advanced topics. The reference for today's lecture are the set of notes by Professor David Sontag. I'll point a link to these in the description box below. Okay, so let's recollect what is the goal of machine learning. Okay, or more precisely, the goal of supervised machine learning. Okay, so the goal is as follows: that we are given some input x, which could be a feature vector. We need to model the distribution of some output variable of interest. Right? Or sometimes we may be interested in computing the expectation of this output variable given the input x. So this output variable, for example, it could be discrete, in which case it's a classification problem. The output variable could also be continuous, in which case it is a regression problem. So the question is that, are these tasks always sufficient? So the answer is no, because there are some tasks which are of more causal nature. Okay, so there are some tasks have an inherent causal nature to them. What do I mean over here? So by causal nature, what I mean is that I need to figure out how does changing the input affect my output variables. So let's take an example for this thing. So let's take the example from medical treatment. Okay. So let us say there is some patient, and the patient has a sort of a medical history and maybe some diagnostic results. We represent these results and the medical history by a feature vector x. Now based on this thing, I might need to perform some sort of a treatment, right? So based on this x, I need to perform, based on this input x, okay, which is the medical history of a patient. So I need to perform some treatment. I can indicate this sort of, let's say that we have two options only, either treatment A or treatment B, or you can even consider it as, something like treatment or no treatment. Let's take it simple. We are considering a binary treatment problem. And the goal is to, figure out what is the effect of this treatment, right? What is the effect of going for option 1 versus option 0? What is the effect of going for treatment versus not going for treatment? So we are looking at the effect on some output variable y, which could be, for example, some later test results, like for example, like the blood pressure or sugar levels. So these are some output variables. So how does performing the treatment affect these output variables, right? So one needs to measure the effect. What happens if one changes the treatment? So the question is that why can't I just go for randomized control trials? So that is not an option always, because there might be some disease which is rare and we might not be able to get enough number of patients. And then also these are very critical. For example, if you are let's say considering a cure for cancer, right, you may not always be able to find human subjects which are willing for that. And more generally, apart from healthcare, let's say it's a problem in economics domain, right? So how does, inflation affect some particular output quantity? So many times these input variables or may not be in our control even. And so that's the other problem. So now how do we tackle this? So one way to go for that is to formalize via this sort of a graphical model. So what's the graphical model we have? So basically we can have some input features, then we can have some treatment or intervention, and then we can have some outcome. Okay. So we can have this treatment variable to be binary, let's say just 0, 1, and we want to see what is the effect of these on my outcome. So outcome is affected both by my input features and treatment. So the way it is studied is that we follow the Rubin Neymann causal model. So here we let y0 as a function of x be the outcome when treatment 0 is applied, and y1x is the outcome when treatment 1 is applied. So we can look at something called as the categorical average treatment effect, or CATE. So this is defined as expectation of y1 distributed as p y1 given x, y1 given x, minus the expectation of y0 distributed as p y0 given x, y0 given x. So this is the categorical average treatment effect. Now based on this we can also define something called as average treatment effect, or ATE, as expectation of x coming from px. Okay, this inner quantity, which is expectation of y1 given as p y1 given x, y1 as a function of x, minus expectation of y0 given p y0 given x, y0 given x. So we can average it over x, and what we get is the average treatment effect. So basically this is the average over the data points from px, CATE of x. Now do I always observe y1 and y0? Right? So the answer is no. So in my observed data, so the data consists of some tuples, which is the input, the treatment, and the corresponding output. So here in my observed data and output, yi is either y1 as a function of xi. So let us say these are xi, ti, yi's, right, I from 1 to m. So it's y1 as a function of xi if my treatment variable was 1, or it could be y0 as a function of xi if my treatment variable was 0. So based on the treatment variable, I either observe y1 or y0. So thus we can write yi in general as 1 minus t1, okay, sorry, 1 minus ti, right, times y0 as a function of xi plus ti times y1 as a function of xi. So basically if the ith observed example has ti set to 1, then I observe y1 xi. If it has ti set to 0, then I observe y0 xi. So what if the treatment is the opposite, right? So that's something called counterfactual. What if the treatment was opposite, right? So here essentially yi is 1 minus ti, okay, this I shouldn't call it yi, right, because this is not an observed variable. So let me just call it ci, right? The counterfactual is 1 minus ti. So if the treatment is 0, then it should be actually y1. And if the treatment is 1, then it should be y0. So the opposite of what is observed. So this is not seen in data. So actually either y0 is seen or y1 is seen depending upon the treatment variable. Now the question is that can we estimate the average treatment effect from the data directly, from the observed data directly? So the answer is no, at least the naive approach does not work. What do I mean by the naive approach? Right. So basically if we look at average treatment effect, so naively one might think that we can just average y1s and average y0s and then take the difference, right, because the data is coming from px. So basically a naive approach would have been that approximate average treatment effect as basically I average yi's for which ti is 1, right. So I just average over those i's for which ti is 1, okay, upon the size of the set of i's where ti is 1 minus the average of those y's where ti is 0. So this could be one possible naive approach. But the problem over here is that here we are essentially taking the expectations over those x's which are where ti is 1, right? So essentially we are not sampling x from px, we are sampling x from p of x given t equals 1, and here we are sampling from p of x given t equals to 0. So basically we are averaging over this xi sampled from this distribution. This is actually incorrect. Okay, so let me write down formally what is happening. So average treatment effect, okay, the way we defined it was expectation of x from px, right, and expectation of y1 is expectation of y1 given x minus the expectation of y0 given x, right. But here essentially x was supposed to be sampled from px, whereas this particular estimator, what it was doing was that it was essentially averaging over x coming from the distribution x given ti equals to 1 or x given t equals to 1 expectation of y1 given x minus expectation over x sampled from t equals to 0 the expectation of y0 given x, and these two are not equal, right, because here x's are coming from different distributions, right. Actually one could have first used linearity of expectations to write it as difference of these two expectations, but then these expectations here are x given t equals 0 and t equals 1, whereas what I wanted was just the x coming from the marginal distribution px. So this is essentially why it does not work, right. So what is intuitively happening is that these t's, which are the treatment variables, these will actually affect the bias the outcome of an estimator which just takes the difference of these two averages, right, because the treatment being set to 0 or 1 was also a decision which was taken during the data, and hence the choice of x's for which t was 0 or t was 1, they will essentially sort of bias this estimator. So what would have been the correct estimator? So the correct estimator would have been sum over I y1 as a function of xi minus y0 as a function of xi over n. Right. But here can we compute this thing? Of not, right? Because we have seen that this requires counterfactuals, because either I have access to y1 or y0. So this requires counterfactual which are absent from data. So this is the problem. So in order to actually solve this problem, we'll actually have to go for some approximations. But before going into the approximations, we'll discuss, what are some of the assumptions we need to make. So the first assumption is called SUTVA or SUTVA. So this model is called as Neymann-Rubin causal model. So what are the assumptions mixed? So first is stable unit treatment value assumption. So what it essentially says is that, if I have two data points, let's say, xi, ti, yi and xj, tj, yj, then essentially, whatever treatment I followed for I will not affect the outcome for j, right? If I is not equal to j, then ti cannot affect yj. And basically every data sample is sort of performing that the treatments are chosen independently, and treatment of one will not affect the output of another. So basically this essentially says is that each data point has outcomes independent of other units. So this is like, the IID assumption we make in machine learning, right? Okay. Proceeding ahead, the next assumption we make is called ignorability. So what it says is that the outcomes y0 and y1 are independent of treatment. Okay, so y0 and y1 are independent of treatment given the sort of inputs x. So basically given some x, I can have y0, it can affect y1, or I can have treatment, but then this treatment will not affect y0 and y1. Now you may find it counterintuitive, because what we saw earlier was that the input features and the treatment were both affecting the outcome y. So right now, how can we say that these are independent, right? Why is not there an arrow from t to y0 or y1? So the answer is that, well, firstly, y0 and y, so the reason why treatment can affect y is that because given a treatment, I can either do y0 or y1. But independently, y0 and y1, like individually, they are independent of the treatment. It's just that if I have to choose a variable y, which is either y0 or y1, then I will need to know what was the treatment which was followed, right? So is this assumption always valid? So that's the question, or it can fail. What do you think? Just write in the comment box below. Okay, so I'll maybe just pause the video and think about it. But just to answer the question, the answer is that yes, the assumption can fail. So in the presence of confounders, so what is exactly a confounder? So confounder is a variable, which affects both y0 and y0, y1 and t. Okay, so there is some variable which can affect t, there is some, and it can affect y0 as well as y1. So because of this, you can see that now there is a path from t to y1 and t to y0 if h is not conditioned upon. So basically it's a new factor which affects both y0, y1 and t. That affects y0, y1 as well as t. So in the presence of a confounder, it's a sort of a, let's say that let's say for example we are just a hypothetical example. I'm not an expert in medical domain, but let's say that there is a treatment which is being followed for a particular patient who has a heart disease, but then the patient also is diabetic. Now the treatment, okay, so X indicates just the medical history of the heart ailments and the current heart diagnostics, but the treatment as well as the outputs are also affected by something else. Let's say the history of the patient being diabetic or not, and the thing is that was not already captured in X, but that was an external factor, and that can be a confounder. So essentially it's a factor which is affecting both treatment as well as these variables, but then it could be that that variable was not taken into account earlier, so that's called a confounder. Now proceeding ahead, we have something called as common support. This is the third assumption. So this essentially says is that the probability of treatment being equal to t given x is greater than 0 for all t in 0, 1. Right? So this is needed to get reliable estimates from the data, because if for some particular x I am always choosing one specific treatment, then I can never estimate the effect of the treatment, right, on the x. If I'm always using treatment 0 or always using treatment 1, then how do I even get an estimate of y1 minus y0? Right? So that's the assumption which we need to make, which is that of common support. So 3 assumptions: ignorability, which means that there are no confounders; common support, which means that all treatments are, they have some non-zero probability of being followed on every x; and stable unit treatment value assumption, which means that the outcomes of each of the independent data points are independent, right? Each of the data points, they have independent outcomes. Okay, so under these assumptions, how do we now approximate average treatment effect from the data? Okay, so goal is to approximate average treatment effect, this ATE, from the data. Okay, so average treatment effect is defined as expectation of y1 minus y0, right? So this expectation over x coming from px and y1 as a function of x, y0 as a function of x. As a function of x, or that could be even like expectation of y1 given x. So it's actually expectation of x coming from px, expectation of y1 given x, y1 given x minus expectation of y0 given x, right? So essentially this equals the expectation of x coming from px, the expectation of y1 given x and t equals to 1 minus expectation of again x coming from px, the expectation of y naught given x and t equals to 0. So why could I add this t over here? This is from the ignorability assumptions. Right. So this is like just the average treatment effect or ATE, right? So from the ignorability assumptions, I could have also introduced these treatment variables over here, right? But what we have access to from this is what we want, and in the data, what I have access to is so expectation of y1 given x and t equals 1 minus expectation of x coming from distribution x given t equals to 0 and expectation of y naught given x and t equals to 0. Right. So this is what I have access from the data and this is what I want. So essentially these two distributions, so here I need to average over px, but what I am able to do is to be able to average from x given t equals to 0 and x given t equals to 1. So what do we do? So there are two ways to overcome this thing. So the first is called as covariate estimates. So here for each x coming from distribution px, so estimate the corresponding counterfactual. Okay, so what is the counterfactual? That is, we need to estimate the expectation of y 1 minus t given x and t equals to t. Right, so basically given x and the actual treatment was t, but what would have been the treatment, what would have been the output if the opposite treatment was followed. And now compute the average of expectation of y1 minus y0 over x coming from px. The question is that how do you estimate this thing, right? How to estimate counterfactuals? So which are not seen in data. So one way is that maybe we can learn some ML classifier, okay, basically an ML, so learn an ML model. For expectation of y given x and t equals to t. Right, so let me just call it some fxt. So what are the possible ML models? Well, the simplest model could be a linear one. Okay. So now a linear model is not always something which would work in practice, especially in today's time of deep learning, but then it's also interesting because it has very nice interpretability, which we'll just see. So a linear model will model fxt as beta x plus gamma t plus some epsilon, where epsilon is some random noise. Now here the expectation of x coming from px, y1 minus y0, is just expectation of x coming from px. Okay, so it's essentially expectation of y. We have seen that this is the expectation of y1 given x and t equals to 1 minus expectation of y naught given x and t equals to 0. So this is expectation over x coming from px, right? And what I have, this is beta x plus gamma times 1 plus epsilon minus beta x plus gamma times 0 plus epsilon, right? So which is nothing but expectation of x coming from px and gamma, which is just gamma, right? Actually there is, so these two epsilons could also be different, but they actually average out to 0. So I should write epsilon 1 minus epsilon naught, but the expectations of these are 0, right? Because these are unit in 0 mean non-Gaussian variables. So this is just gamma. And note that here KATE, right, or categorical average treatment effect, that is the quantity inside this expectation also is gamma, right? The expectations, once I take it, it's also gamma. So it has a very nice interpretability because the coefficient for the treatment variable, that itself is my average treatment effect already. So just learn a linear model and the coefficient which you get is the average treatment effect. So it looks interesting, but then it might not be the right thing always, and you might need more complex models. So one way is that you can also take a neural network. So neural network which you take, the main thing is that the goal is not prediction over here. It's not a machine learning problem. It's a causal inference problem. So the goal is to see the how the outcome T is affecting, how T is affecting my outcome. The goal is not that, to get the best possible estimate. So one must also take care, that actually my treatment variable is actually taken into account. So one possible model could be, that first learn a common representation of x, and then have a sort of two different networks attached to it, one wherein the prediction is for t equals 1, the other could be where the prediction is for t equals to 0. So you have a neural network wherein you first get a common representation, and then you have two sub networks, one predicts the outcome for 0 and the other predicts the outcome for 1. This is the neural network thing. The third approach could be, that could be sort of a matching approach, which is like the k nearest neighbor. So for each data point xi, so compute its nearest neighbor xj, amongst all j such that tj is not equal to ti, or tj equals 1 minus ti. Now we estimate the average treatment effect as the expectation over x of y1 minus y0, which is sum over I such that ti equals 1 yi minus y of fi, okay, plus sum over I such that ti equals to 0. So basically fi is the nearest neighbor, right? So we are denoting j by fi. So j is the nearest neighbor which has the opposite value. So if ti is 1, I'll take the difference between y1 and y0, which is yi minus yfi. If ti is 0, then I'll take the difference between yfi minus yi, and then I'll divide it by the total number of points, which is n. So essentially this equals sum over I 2ti minus 1. So there is either a plus sign or a minus sign with yi minus yfi. So if ti is 1, then there is a plus 1. If ti is minus 1, then there is a minus 1. If ti is 0, then there is a minus 1 sign. So to convert 1 0 to plus minus 1, I have this 2ti minus 1 factor. So this is an estimator for average treatment effect. So basically for every point, compute its nearest neighbor with the opposite treatment, and then just compute this quantity, right? So this is a very simple approach. It's non-parametric. You don't need to learn any parameters. So it might generalize if you have lesser amount of data, but then the thing is that the accuracy might not always be that good, because for some points there might not be a matching point which is close by. So this was the first set of approach called covariate estimates, which means that I estimate a corresponding counterfactual for each point. Okay. The second approach is called as propensity scores. So in case of propensity scores, one can do something called as importance sampling. So essentially the idea is that the main issue was that this expectation which we had, right? So we can compute the expectation provided the points are coming from the distribution px, but then the data has the distribution x. The data is averaging y1 given x t equals 1 and y0 x t equals 0 from two different distributions. One is x given t equals 1 and x given t equals to 0. But what I want is that this sort of difference. So it's the same expectation, except it's over a different distribution. The quantity inside the expectation is the same. So this might remind you of something called as importance sampling. So in importance sampling, what you have is that let us say that there is some random variable x which comes from some distribution p. Okay, but what I want to compute is that the expectation of the same random variable, right, but from some distribution, let us say coming from q. So what I can do is that it's essentially fine, but let's say the samples I have are from a distribution p, but I want to compute their average as if coming from q. So this is essentially one way to go for that is that let's say that I take the distribution from p, but then I also multiply a factor of qx by px times x, and then you can show that these are equal, right? Because essentially this is going to be integral over px qx by px x dn x, which is the expectation of x given qx. So essentially if I want to change the distribution, I just need to add this particular factor, which is the factor of importance sampling. So essentially in our case the ATE, right, which we want to compute, is expectation of x from px, expectation of y1 given x and t equals to 1 minus expectation of x given px, expectation of y0 given x and t equals to 0. So the idea is that these expectations I'm averaging them over x, but the idea is that if I want to sort of average over, so the data has expectation of y1 given x and t equals to 1, but from x distributed as x given t equals to 1. Similarly, it has access to y0 given x and t equals to 0, but from the distribution x given t equals to 0. So how do I reconcile these two facts? So the idea is that I can weigh the samples by probability of x over probability of x given t equals to 1 and probability of x over probability of x given t equals to 0, right, and then take these averages. So that gives us, okay, but by the way, probability of x given probability of x over x given t equals to 1, this can be expressed as probability of x times probability of x comma t equals to 1 over probability t equals to 1, right, which is nothing but probability t equals to 1 over probability of t equals to 1 given x, right, because if I take this to denominator, x comma t equals to 1 over probability of x, that will give me probability of t equals to 1 over t equals to 1 given x. Similarly, this will be probability of t equals to 0 over probability of t equals to 0 given x. So the only change is that now I can have the average treatment effect as expectation of x given t equals to 1, right, because this is the sort of thing I can estimate from the data, y1 given t equals to 1 and x times probability t equals to 1 over probability t equals to 1 given x minus the expectation of x given t equals to 0 of expectation of y naught given t equals to 0 comma x times probability of t equals to 0 over probability of t equals to 0 given x, right. So I can now write it as sum over I such that ti is 1, probability of t equals to 1 over t equals to 1 given xi times yi, and I normalize it by the set of indices where t equals to 1 minus I such that ti equals to 0, and sum over I such that ti equals to 0, probability of t equals to 0 over probability of t equals to 0 given xi times yi, right. So which is here I'm averaging y1, here I'm averaging y naughts, but then I'm also having this particular factor. So how do I get these factors? Well, we'll need to estimate probability t equals to 0 and t equals 1. This is easy to estimate, just the empirical frequencies, and I can take the sort of normalization, and for t equals to 1 given x and t equals to 0 given x, we can learn some classifier. So these are some of the basic techniques which we have discussed today. If time permits and if there is interest, I might go into some of the advanced techniques and the recent papers on this topic. Okay, thanks a lot. Bye.